Dear participants, we are resuming the next session, and we have with us Professor Abhijit Abhyankar to deliver a talk on electricity markets in the era of large-scale renewables. He is NTPC Chair Professor in the Department of Electrical Engineering at IIT Delhi. He has been an expert member of various committees established by the Central Electricity Regulatory Commission, National Reliability Council for Electricity, and Central Electricity Authority. He has served as a special invitee in a subgroup on reserves and ancillary service at state level under Forum of Regulators Standing Technical Committee. He is an expert in power system analysis and optimization, issues in restructured power systems, distributed systems, policy and regulatory matters, smart grid, and transmission system flexibility. With this, we will welcome you, sir, and request you to start the lecture. Thank you, sir.
Sure. Thank you. Thanks for the introduction. Namaste to all of you. Good morning. Let me just share my screen. Okay, so right. So can somebody tell me if my screen is visible and that I am audible?
Yes, sir.
Great. Thank you so much. Right. So thank you, Professor Priyanka Kaushal, for inviting me to deliver a talk in this ITech online short-term course on energy systems and carbon neutral economy. So the topic of my presentation today is electricity markets in the era of large-scale renewables. And I welcome all our guests from the participating countries. And I hope that through this talk, you'll be able to gain some idea about the Indian power system state and certain aspects of electricity markets, not pertaining only to Indian electricity industry, but overall. Now, this is going to be 1.5 hour talk, and the focus of the talk is going to be on understanding certain aspects of renewable markets in the context of renewables. What exactly are the challenges that are posed by the renewable energy resources, so long as system operation point of view is concerned? What are the market architecture and design issues? We'll see that in this particular talk. In the meanwhile, if you have, if you find that there is something wrong with my presentation, I mean, if you can't hear me or if my slide is not visible, please do let me know, and I'll try to improve. And if you have any questions while the talk is going on, you're most welcome to ask. I would prefer that you put your questions in the chat box so that I could answer them after my talk is over. Yeah, so let's start. So I'm on slide number 2, and the slide shows the contents. What is this talk all about? I'm going to start with the energy transition trends. Now, when I say energy transition trends, we must understand that the way in which the electricity is being utilized by the end user, the context and the dimension of the same is going to change in the future, near future, and of course in large scale in long term. So we will see what exactly these energy transition trends are there and how are they shaping electricity industry. Then we will see what is meant by ancillary services in conventional power system operation parlance. And once we talk about ancillary services, let us have a look at the peculiarities of electricity as a commodity. What exactly is meant by this particular commodity, and how is it really, how is it different from the other commodities available in the market, and what bearing it has overall, so long as system operation is concerned. That we will see. And this will take us to the relevant next topic, that is market architecture, electricity market architecture. We'll see certain aspects of electricity market architecture over here. And then we will shift our discussion to the discussion on the distribution systems and their operations, and how the context of distribution system operation is going to change once you have large scale renewables getting integrated into the system, that we will see. What are various electricity commodity markets and how do we coordinate between them? Like, for example, you have a certain set of electricity commodities available within the distribution system and a set of commodities available at the transmission system. How do they coordinate with each other? That we'll see later. And towards the end, we'll devote a couple of slides. We'll see discussion on the Indian perspective, so long as these markets are concerned. Let me start with energy transition or the energy transition trends that are shaping electricity industry. So there are these 5 aspects that you will see, which kind of create or they change the dimension of the overall electricity industry and electricity markets. First is you have increasing electrification. That means nowadays you will see that there is a lot of thrust that end user is giving so that it utilizes electrical energy for certain utilities. For example, if you look at the buildings, then the conventional heating and cooling requirements of building, at least in European countries, now there's a lot of talk that they should be moving from the conventional gas-based heating or cooling to electricity-based cooling. So there's going to be a quantum change in the consumption of electricity so long as buildings are concerned. Mobility, all of you know that nowadays everybody is talking about electric vehicles. So we expect that there's going to be a large scale change so long as mobility is concerned. People will migrate to usage of electric vehicles, and there's of course going to be a cross segment optimization or cross sector efficiency that will be talked about. Industry, all industry needs, they will be converted from basically the heating and other requirements. Now they will be converted into the electricity usage. So increasing electrification is one such energy transition from utilization point of view, which is shaping electricity industry. Then there is second aspect, that is growth of green technology. Now you can see that you either have these days large scale utility, large scale renewable generation, or you have distributed generation in terms of solar rooftop and whatnot, right? So idea is to provide clean electricity for the end usage, and there's a lot of thrust that is being given on this particular aspect. If you look at the future networks, which would cater to the ever-changing needs of demand for this electricity, the future networks are supposed to be, by and large, or in larger context, they should be called as resilient grids, because the dependence of the consumer will be more and more on electricity henceforth, and you must have a grid that is resilient, self-filling in quick, no time. That is the characteristic that you should assign to the future grids. The future networks will also have inherent flexibility embedded within them. this inherent flexibility is something which by and large might come from storage or other demand response or EV aggregation, etc. How do we exploit that? There's a lot of discussion going on, and how do we make it useful for the system operation, power system operation, that is being discussed amongst the researchers at great lengths. The cities now, they are turning into smart cities. Basically, there is a smart and sustainable transition, and that through cross-sector efficiency. For example, if you have now EVs, then there is a cross-sector coupling that is happening, and overall efficiency will happen so long as automobile industry is concerned and battery industry is concerned. So you have to take that into account. So this is something that is shaping the new electricity usage trends. You also have consumer activism. The consumer has changed. The demands from the consumer, they have changed. Now you have consumers who expect new values beyond price. It's not only the cheaper resource of electricity, but then there are other values that consumer wants beyond the price. For example, power quality, reliability, and whatnot. Then there is a digital expectation. The interaction of the consumer with the utility has taken a digital turn, right? So now we don't go to the utility office anymore. Rather, the utility office is available on our desktop for all types of services. And day by day, a day will come when there'll be no physical utility corporate office per se or commercial office per se where the transaction is being done with the end consumer. All will be virtual in a way. And the consumer will very soon have greater choice. If you look at the mobile companies, the explosion of mobile technology and the commercialization of the same, if you look at it, similar transition is expected few years down the line in electricity industry in many countries, where you will have multiple retailers who would be bidding for getting hold of various consumers. Now, all this will have the backbone of digitalization, and that is supported by strong communication network, IT solutions, and whatnot. So this is the new trend that is happening so long as energy consumption is concerned, and it is supported by strong digitalization. Now, all this change to energy usage is supposed to be brought through the usage of clean technology or clean electrification. So you cannot just keep on burning fossil fuels to serve the increased demand from the utilizers of the same. Rather, you should look for the clean electrification of the end usage. Now, what is happening these days is that everybody is talking about clean electrification, considering the environmental considerations. But when people talk about clean electrification, I feel personally that there is certain level of myopic way of looking at it. That means people look at the clean technology generation through clean technology, which serves a set of loads or consumers demand in terms of energy. So you require this much of energy and then this much of generation through clean technology. That is what is being discussed. What we must be thinking of or should be observing is a very critical aspect called as grid operation and infrastructure. There is a whole grid in between, transmission grid, transmission distribution network between the generation and the loads or the consumers that you have. It is another thing that distributed generation is coming up in a large way, but there's still ample time to go before we have fully decentralized or distributed set of local generation available. Right now, and even in the near future, we are bound to have large scale large scale generators, which could be located far away from the loading itself. So you have grid in between, and grid operation poses a real set of challenges. Now, what are those challenges? Let us have a look at them. So let's say you have enough capacity installed, so long as utility scale renewable energy sources are concerned, which could be wind or solar PV, etc. And you have on the right hand side, you have a set of loads, right? Now, the discussion from the planning point of view that we do is energy to energy mapping. That so many million units required, so many million units generated through green technology or RES, renewable energy resources or sources. Now, when you change the discussion from the energy perspective to power perspective, the things start changing. Because when you start talking about the power requirement rather than the energy requirement, the grid operation is a real challenge. For example, let's say you have a set of wind power generators, solar PVs, and you have a set of conventional thermal power generators as well. Okay. Now, question is, how much of thermal power generation, conventional thermal fossil fuel based thermal power generation should be in place? Do we really need it or not? Of course, we need it because of the inertial requirements. Now, one must understand what exactly is meant by inertial requirements. So those who have good grip on power system operation, they can very well understand inertia is required because so you don't have control per se on the system, on the load in the system. The consumer may switch on off various utilities as per the whim and wishes of the consumer. Now, utilities from generation side, you cannot quickly change manually those, the generation so that it matches with the load in the system. For conventional fossil fuel based thermal generators, the rotating masses, they store the kinetic energy. And whenever there are changes in the balance between load and generation, this balance is met, is compensated. Whatever is the change is compensated through this kinetic energy that is stored in the rotating masses. This is called as, in simple terms, called as inertia requirements. So now the idea is that you should keep the frequency constant. In your system, you can't allow frequency to deviate to a great band because it has got its own ill effects. So you want to maintain frequency at the nominal level, for example, 50 Hertz in India. And these rotating masses, they take care of small changes that happen so long as load generation balance is concerned. So you need conventional rotating masses based generation in the system. Question is how much of them? And that really answering this question is a real challenge. Now, recently in the last week itself, in COP26, all of you must have observed that India is being criticized for changing the wording in the notification or the announcement. The wording earlier was phasing out of coal in the system. And it is said that India wanted it to be phasing down of coal. Now, those who have been involved in power systems, I don't know if anybody has got that background in the audience at this stage in this particular class, but then those who are involved in power system operation, they would really appreciate the existence of rotating masses in the system, which provide inertia so that the system frequency is maintained. Otherwise, the system can go haywire. So in my opinion, the change from phasing out to phasing down of coal is very useful, and time will tell that it was a very welcome move. Moving on, let's see another case that whenever you have on the left hand side, you can see that you have solar PV panels, and let's say all of a sudden there is a cloud cover. So for monsoon dominated countries like ours, like in India, during monsoon season, you have what is known as shadow effect. It might so happen that a large scale solar farm might get covered through a large set of clouds, and all of a sudden that total solar generation is gone out of grid. So it could be 50 megawatts, 100 megawatts, or it could be more than that as well. That can happen, and all of a sudden once the cloud passes, you can have that generation getting injected into the grid. Now, so long as the changes are small, when this solar generation is into the grid or out of grid, if the changes are small, those can be taken care of with the inertia requirements of rotating masses. But if the changes are large, as I explained just now, what is going to happen is that you will have to ask the conventional generators. It may not be conventional generators, other sources of generators, to do ramping of the same. So let's say all of a sudden a solar farm is out of picture. You will ask a set of conventional generators to ramp up so that there is a load generation balance. But if let's say once that cloud passes over and this solar PV is exposed to sun, again that solar injection will come into picture, and then you will have to ask ramping down of these conventional generators, right? So this is a challenge, because the conventional generators, they have got finite ramping capability. The ramping capability is the physical characteristic of your generation, and you just can't ask a generator to change from one level X to another level Y in a jiffy. You will have to give certain time. There are certain time constants involved, and then the generator would increase in or decrease in by using certain ramp rate, right? So yeah, so this ramping may or may not be sufficient. That can be a challenge. So you have to take into account how much of ramping capability do you really have, and that will decide the flexibility of the system. So what you have to keep in mind is that if you have large scale renewables embedded into the system, then in that case, these renewables being variable and uncertain, these two aspects are very important. Variability and uncertainty of these renewables creates a lot of challenges in front of the system operator. How do you really handle them? That is the question. Now, in the changing context of energy transition, the demand can also be made a control variable. That is an added bandwidth or added leverage that system operator is likely to have when you have the changing utilization pattern. So you can make demand a control variable, how we will see a little later, right? So what you have to keep in mind is that only adding renewables, adding plants is not sufficient. With it, it brings along a large range of ancillaries involving technology, redefining operational practices, change of infrastructure, and changes in policy and regulatory considerations. So that needs to be kept into mind before we take any decision. Now, let us have some more insight into the aspects of system operation, and then let us try to link it to the market consideration later on. Now, here you have a bus. It's a bus bar. Those who are not those who do not have power system background, for them, let me just explain. This is a substation, electrical substation. The horizontal line is a substation, and A and B, these are, let's say, two generators, generating units connected at this bus, and there is a load connected to it. So basically, it's a secondary of transformer. There can be multiple types of utilization connected below this load. Okay, so I'm taking the abstracted or bird's eye view of this particular bus. Question is, how much load can be handled securely? Now, this word securely is very important, because when I say word securely, I am talking about the reliability aspects. So the answer, if you try to say that answer is 200, let's say megawatts of load can be handled securely with this system, the answer is wrong, because the power system operation usually happens with n-1 consideration. That means you will operate the system in such a way that even if one fatal contingency takes place in the system will continue to run in secured way. So this n-1 consideration, if you apply over here, then the answer to the question that I have shown over here is 100. What it means is that even if one generator fails, one generating unit fails, the demand of 100 can be catered to using the second unit as well, considering the n-1 criteria. Now, different systems, they have got different reliability criteria, n-1, n-2, n-1, and so on and so forth. Let's have a look at another case. I have a group of generators and I have consumption. Now, this consumption is made up of solar PV panels, conventional buildings, battery storage, you have electric vehicles, aggregators for the same, and it's a heterogeneous kind of utilization that is happening. Now, what happens is that, let's say from the system operation point of view, the forecasted consumption is 1000 megawatts. I'm taking some random number just to explain my point. So as a system operator, what I will do is I will schedule this 1000 megawatt load with 1000 megawatt generation with certain resources shown over here, group of generators. Now, this is scheduling part. So I'm asking generators to be ready with 1000 megawatts. And I have certain kind of contract with them, let's say. Now, in real time, what happens is that the consumption might end up having 1200 megawatts. Now, the question is, which generators should provide for these 200 megawatts? The question becomes important, especially when you have markets in place. Let's say the entire demand in the system is catered through market mechanism. Now we are in deregulated era. The entire consumption gets its power through market mechanism for, let's say, 1000 megawatts, which is over there. But as I said, there is no control over the utilization part of it on many aspects, because the load aggregator may not have direct final control over what is being or how much is being used. That is number one. Number two, you have variable resources like solar PV embedded into the distribution system. So depending on their uncertainty, the real-time consumption is likely to change. Now, if there is a deviation between the scheduled generation and the actual consumption, then how do you really make up for those 200 megawatts? That is the question. And in what market method or market mechanism, how do you really acquire those 200 megawatts? Does that mean that if you don't have this, if you don't schedule or make a contract with this for this extra 200 megawatts, will you not be able to get the supply? No, that's not the thing. You will continue to draw the supply. You will continue to draw to 1200 megawatts. Question is, how do you compensate for those 200 megawatts? This requires discussion. This requires discussion because it falls under the aegis of what is known as ancillary services. The provision of ancillary services is much talked about topic, especially when you're working in deregulated environment, when you have markets for various electricity commodities. Now, what if you don't provide for appropriate set of ancillary services? So compensating for those 200 megawatts is one kind of ancillary service. Now, there is a report by NERC which tells you that there are 12 basic types of ancillary services. So this is one of them, that if there is a deviation in terms of what is scheduled and actually consumed, how do you make up for that deviation? So that falls under the hold of ancillary services. What if you don't provide for those ancillary services as system operator? If you leave everything to market, then what is going to happen? So as a system operator, let's say you decide that let consumers go to the marketplace and buy from generators at their price requirement, and I'll just sit quiet. That is not going to happen, because the system operator will always want or will have to provide for what is known as ancillary services. If you don't provide for them, then you have power quality effects, that is frequency variation. Now this frequency variation, please keep this in mind, that it has got direct bearing on the load generation balance. If the generation is more than load at any given instant, the frequency will start rising. If the load is more than generation, the frequency will start falling. And as a system operator, you will have to arrest that rise or fall of the frequency by invoking appropriate set of ancillary services. There will be voltage fluctuations. You need to maintain voltage as a system operator within certain band. So these are power quality effects. What are catastrophic effects? If you don't give much heat, pay much heat to the effects that are being caused because of the deviations, it may lead to what is known as blackouts, right? And all this has got commercial implication. All of you know about it. So you need to provide for ancillary services. So this is the definition. Ancillary services are defined as all those activities on the interconnected grid that are necessary to support the transmission of power while maintaining reliable operation and ensuring the required degree of quality and safety. That's the definition of ancillary services. Now, why are we discussing ancillary services in depth? Because I want to link it to the market considerations. But before talking about the market design and market architecture issues, so long as electricity is concerned, we must first understand the distinguishing features of electricity as a commodity. Now, when we talk about electricity, which is a commodity being traded in power marketplace, before drawing any conclusions or trying to understand any modalities, we must understand that electricity as a commodity has got altogether a different set of characteristics associated with it. You cannot compare electricity as a commodity with any other commodity in the market. That is just not possible. Why? Because these three distinguishing features of electricity as a commodity. What are these features? One is that this commodity should exhibit real-time demand and supply balance. What does that mean? That means you will produce electricity as and when it is required. You cannot produce electricity in bulk quantities and store it somewhere and then use it when it is required. Now, it is another thing that battery storage is being discussed these days, but then battery storage compared to the overall consumption of electricity in large scale grid is concerned, the battery storage is a minuscule amount, right? So you cannot store electricity in large or bulk quantities and pass it on to the load when it is required, right? For other commodities like soaps or toothpastes or mobiles, you can produce them in bulk in manufacturing plant and dump them in warehouse, okay, and send it to the user when as and when required. That cannot happen with electricity. There has to be a real-time balance between the demand and supply. Number one. Number two, power flows, they obey laws of physics. This is very important. I have a generator located at some location and I have a load or consumption of the same located at some another location. There is a grid in between. Now, the way in which this power flow takes place, power flows happen all across the grid. It is decided by laws of physics. You cannot ask electricity, flow of electricity or flow of current to take a certain path. That cannot happen. It goes by laws of physics. What does that mean? That means you don't have direct control over flow of current on transmission lines. And this poses different challenges in terms of congestion. Okay, we'll talk about that. For other commodities, what is the scene? For other commodities, you can always take out commodities from the warehouse, dump them on a truck and ask truck to take certain path so that dispatch is done. That does not happen with electricity. And the third distinguishing feature, very important, of electricity is that given a generator of electricity, there are multiple commodities that it generates. And there are compatibility and interactions between those commodities. Single generator, multiple commodities, they come into picture. That is very important. So combining 1, 2, and 3 distinguishing features of electricity, what happens is that there is unusual variations in the prices of this commodity. So if you leave it to the market to decide on the prices of electricity, because of 3 distinguishing features of the same, there is an unusual variation in the demand, and which is the characteristic feature of this electricity as a commodity. No other commodity has got such tremendous price variation as such. Okay, right. Now let us see cause and effect of the same. When I say there should be real-time demand and supply balance, what is the effect of it? Effect of the same is on 2 operational aspects. One is the scheduling and dispatch activity, and other is the imbalance activity. So this is the explanation that I gave you earlier through one example, that you schedule for certain quantity, but then imbalances might happen, and because you want to serve or satisfy the load generation balance online, you need to make provisions for the same. So there is a day ahead consideration of scheduling the generators either through dispatch protocol or through markets, or you can have and then you can have real-time activity, which in many countries happens to be market based. Then second characteristic, that is power flow obeys laws of physics. The effect of the same is network congestion. So since you don't have direct control over the flow of current, what might happen is that if the end consumers end up making contracts long-term or through power market, short-term power market, with a particular generator which is very cheap, offering very cheap source of power, then the power being dispatched through that generator flows on a particular set of transmission line, and that transmission line may get congested, and you cannot allow congestion to take place. The protective system on the transmission line will open that line, then the flow will get transferred to some other line, and there can be serial cascading of the transmission lines, which can lead to blackouts. Second commercial implication of the same is that the system operator cannot arrange arbitrary set of transactions. This is what I said. So all loads going to one single cheap generator, that might not happen because of network congestion being in picture. That is the effect of the same. Then the third part, that is generator product compatibility and interaction. So the same generator can produce megawatts or MVARs, that is reactive power. So these megawatts, when I say megawatt of electrical energy or electrical power rather, this has got either energy context or reserve context or regulation context. What it means is that a single generator's total capacity can be divided such that a portion of the same can be asked to provide energy. A portion of the same generator can be asked to be prepared under reserve category, or a portion of the same can be asked to be prepared under regulation category. That can happen. Now, effects of these peculiarities is that it leads to 4 pillars of electricity market design. Now, these 4 pillars of electricity market design, they are very important from the discussion, from the implementation point of view, so long as market is concerned. Look at any market design across the globe, you will see that these markets, they give due respect to these 4 pillars, and the design is done in such a way that a set of, there are certain practices that are evolved to take care of this, of all these pillars of market design. What are these 4 pillars? One is imbalance, second is scheduling, third is congestion management, and fourth is ancillary services. So these are 4 pillars of market design, and then these have emanated from the 3 basic differentiating characteristics of electricity as a commodity. Now, what do these pillars of market design, how do they affect the market design per se? Let us see. The market design creates different commodities so long as trading of electrical energy is concerned. What are those commodities? Those commodities, they pertain to energy, which is obvious, but then you want to transfer power from one place to another. So the transmission corridor becomes another precious commodity, right? It might so happen that there is a limited corridor available, then one who is ready to pay more for that can get that corridor allocation. That can happen under the market environment, right? But then you have to have appropriate market design in place to take care of this. Now, with this different set of commodities coming into the picture, the market architecture gets a very important, gets a lot of importance. What is market architecture? Market architecture is a map of its component submarkets. Now, within electricity market, you must understand that there is nothing like single electricity market. Along with it, because of the distinguishing feature of electricity, there are multiple submarkets associated with it. And this map includes type of each market and linkages between them. How are these different commodity markets of electricity? They are interlinked. How are they placed? The question is, why do we need multiple markets? That we have already answered. The answer can be traced back to peculiarities associated with electricity. There are three peculiarities associated with electricity, which kind of give rise to 3 broad-based commodities in the market. And the 4 pillars of market design tend to cast the same electric energy into various products. That is what you should keep in mind. And then these various products lead to different markets, which I call as sub-markets of electricity. So what are these sub-markets arising due to 4 pillars of market design? Imbalance energy market. They lead to what is known as spot market. So from the designing point of view, the rules of spot market, they become very important. A couple of rules I can tell you. What should be the gate closure? Because there has to be certain gate closure beyond which you cannot allow the entities or stakeholders to build into the market, right? And then what could be the quantum, minimum quantum? Can you allow a particular market entity to bid for 1 kilowatt hour, or it should be 1 megawatt hour or 10 megawatt hour? There are certain rules of spot market which has got bearing on certain different aspects, granularity and all that. Then there is a transmission capacity market which comes because of this congestion management, and there is a whole set of ancillary services market. It could be reserve, it could be regulation. Within the regulation also, within the reserve also, you will have multiple markets like 5-minute regulation, 10-minute, 5-minute reserve, 10-minute reserve, and whatnot. So this comes under the fold of ancillary service management. So all in all, broadly speaking, there are 4 power sub-markets: wholesale spot market, wholesale power market, market for ancillary services, and market for transmission capacity. Now, you must understand that when you have large scale renewables getting embedded into the system, these markets, and rather the ancillary services markets, they get a lot of prominence. Why? Because of the characteristic of your renewables. They are uncertain and variable. Now, as I have explained in earlier, one of the earlier slides, whenever there is change in the nodal injection of the generator, that happens because of the variability and uncertainty of your renewable generators, the same should be compensated by some other set of generators, which could be conventional generators, right? Now, depending on the disturbance that might get introduced because of this variation in renewables, a certain set of ancillary would come into picture. Ancillary service from conventional generator would come into picture. So what could be those different ancillary services, and what could be their pricing mechanism is a real regulatory challenge which is being discussed all across the globe. There is a special regulation that that FERC came out with, which incentivized the battery storages. I'll just come to that part a little later, and I'll explain how batteries are useful, especially when you have renewables in the picture. So keep in mind that when you have large scale renewable generators, the commodities which fall under the aegis of ancillaries, they really are very important, and a lot of work needs to be done so as to design the ancillary service markets when you have large scale renewables. Now the question is how these sub markets are arranged. So by and large, as I said, there are three types of markets. One is imbalance energy market, transmission capacity market, and ancillary services market. Now, one way of looking at this is that you settle or clear these markets rather in integrated fashion, and that is known as centralized dispatch. So the structural interlinkages between these types of different markets, like the impact of congestion on the energy market clearing, or the impact of energy market clearing on various ancillary services, etc. These, if you bind all of them into one market clearing process or framework, that is called as integrated arrangement or centralized dispatch. There's another way of looking at it, that is option 2, sequential arrangement. Now this sequential arrangement, what is done in this is that various commodities or various sub-markets, they are cleared in sequential fashion. For example, what you do is you first clear the imbalance energy market, which is a spot market, then take the outcome of this spot market, go to the next level market, that is transmission capacity market, superimpose the outcome of imbalance energy market on this transmission capacity market, clear the transmission capacity market, and take the results of the two to what is known as ancillary services market. And then once ancillary service market gets cleared, you have outcome of the whole process, and this approach is known as centralized dispatch. So in this approach is known as decentralized dispatch. Now the centralized or decentralized dispatch, what happens is that the buyers and the sellers, they provide bid into the market, and there could be some long-term forward contracts, physical delivery markets, or the financial markets. And this dotted square is something where all this data is fed, and there is one joint optimization carried out by system operator, and the outcome is available for scheduling. So this is a block diagram of central optimization that system operator carries out so long as clearing of centralized dispatch market is concerned. Now, what is the input for this central unit commitment or central optimization part? The entities, they provide data associated with complex bits. Now, what is meant by complex bits? You have to understand that the system operator in this case is clearing all markets, keeping in mind the power system compliance. That means whatever is the outcome of this central block will be power flow compliant, power system compliant. There will be no violations of any sort so long as system operation is concerned. Obviously, from system security point of view, this is something that is very preferred. The complex bits, they involve two types of information to be fed to this central block. One is the commercial bit, where the load can say that if the price is X, I am ready to please schedule it for me, please schedule me for Y. If price is K, then schedule me for J, something of that sort. Exactly similar bid is posed by the generator itself. But the generator will also, along with that, provide various type of information, right? Like what will be its bid for regulation market, along with energy, which forms part of this complex bid. What will be its bid in regulation market? Then what are its technical parameters so long as ramp rates are concerned? All this information is supposed to be provided by generators to this central calculation. Then there are different reserve requirements, reliability aspects that are fed into the system, into this particular block, and there is a central optimization that is carried out. And the outcome of this is real power dispatch, reactive power dispatch, and locational marginal prices. So in central optimization, please keep in mind that all sub-markets, the architecture is such that all sub-markets, they are cleared simultaneously. In decentralized dispatch, as I said, there are different blocks. Energy market is solved separately, ancillary is solved separately, congestion is solved separately, and then things are scheduled. And sellers and buyers, they provide bid into energy market, If there is a market for ancillary, then they provide separate bid and so on and so forth. Now, what you must understand, this is very interesting slide. What you must understand is that the whole world is divided into two parts. One which follows centralized dispatch philosophy, and the other that follows decentralized dispatch philosophy, or the integrated and decentralized way of market clearing that I had shown you earlier. On the right hand side of this dotted boundary, the world is dominantly decentralized dispatch. That means you don't have integrated way of clearing the markets. Rather, the markets are cleared in stepwise fashion, right? On the other hand, on the left-hand side, basically North American power systems and power markets, they work on dominantly on what is known as centralized dispatch philosophy. Okay, in India, we follow, so long as scheduling is concerned, it is more of a decentralized way in which distribution system operators, discoms rather, they get the requisition based on their future forecasted requirements from the generators, right? But then there are interlude layers of central and decentral calculations. So it's kind of hybrid system, I would say, but by and large, it's a decentralized dispatch. All ISO, the European countries work on the similar principle, but all independent system operators in US, they work on centralized dispatch philosophy. Now, the major difference over here is that in centralized dispatch philosophy, the independent system operator in itself, he or she himself is or herself, they are the market operators. The system operation, market operation, they are integrated in centralized dispatch philosophy. In decentralized dispatch philosophy, the market operation is with a different entity. The system operation is with different entity. And they interact with each other to come out with the outcome of the market clearing. So that's the difference. Right. Now, let us see. So we have got fairly good idea about the market design, sub-markets, and market architecture, etc. Now, the buzzword around the world is storage these days. Okay, battery energy storage or different types of storage. People are also talking about hydrogen. Okay, this storage thing has got a different dimension altogether, so long as system operation and power markets are concerned. Now, why this storage have come into picture? Why were they not in the picture earlier? One is the technology development, number one, and number two is need driven. So, as I said, if you have large scale penetration of renewable energy, that means your system is more vulnerable to changes in the generation provided by these renewables, which are uncertain and variable in nature. Now, in order to quickly compensate for them, you need quick response mechanism for the compensation. And this comes from what is known as energy storage systems. Why are they quick? Because the difference between a conventional rotating mass-based thermal generator and battery is that the rotating mass-based thermal generator will have inherent time delays so as to ramp up or ramp down its generation capacity or input into the system. On the other hand, for batteries, it is as good as instantaneous. You change the power order and it will change suddenly whatever is the power requirement without much of time delays. So the sudden changes that would occur because of, let's say, shading effect of solar PV, those can be quickly compensated by your batteries, but not with your conventional generators. The conventional generators are important from the inertia point of view, but to provide quick compensation for the changes in renewable energy output, you need batteries in the system, or rather the energy storage in this system having high ramp rates. And that's why there's a lot of discussion that is happening. There's a lot of energy penetration, that energy storage penetration that is coming up all across the globe. So let us quickly have a look at energy storage installation. So there's an exponential growth in energy storage system installations. About 8 gigawatts in US, 4 gigawatts in China, 3 gigawatts in Japan by 2022. So all in all, it is expected that we'll have 40 gigawatt of installations globally by 2020. But that has not been achieved because of various reasons. This will, I don't have exact numbers with me right now, but the projections were there about 3-4 years back. Now, the PJM, that is Pennsylvania, New Jersey, Maryland interconnection in US, it projects $25 million savings due to reduction of 10 to 20% capacity procurement. Now, as I said, to compensate for the variability, the system operator needs to make a contract with the system operator or with the generator for buying capacity for providing ramping up or ramping down within certain range, right? This is called availability, buying capacity or making generator available to provide for the compensatory action. The system operator is supposed to make payments for the same, right? Now, instead of buying this capacity on rental basis, if the system operator invests as part of capex in installing energy storage systems, that would be beneficial. That's the thought process in PJM and some US systems. What are the usages of energy storages? Renewable support. That means if you have renewable farm, it can be complemented with the system storage, energy storage system, so that overall at the point of common coupling, their schedule does not get deviated. So if it has committed for certain power output or consumption, it will maintain at that, because whatever are the vagaries of generation of renewable can be compensated by associated energy storage systems. It can be used for distributed storage, demand side management, and various ancillary services. Basically, it provides for the flexibility in the system. So when we talk about energy storage systems as ancillary services, there are 3 types of ancillaries that it can provide. One is frequency regulation. Excuse me. One is frequency regulation, which can provide fast ramps, lesser cycling of conventional generators. Now, one thing you must understand is that when you have large scale renewables coming into the picture, because of their variations in their output, if you ask the conventional generators to provide for the compensatory action, what it means is that you are asking the conventional generators to do cycling. Okay. Now this cycling is harmful for these thermal generators because their life reduces because of this cycling. So a 25-year plan, if you the plan designed for 25 years, if you ask it to cycle more often, its life will reduce. Okay, so you don't want the conventional generators to cycle quite often, and hence these battery storages can be of great use. You can use them for reserves that will lead to reduction in capacity procurement, which I just explained, and this can be used as black start as well. So when system goes into complete collapse or blackout, it cannot just start like this. There is a standard, very complex and painful process through which you energize the whole system, and that's called black start. And those generators which provide this facility, they are called as black start. So the batteries can provide for the same. Now, what are the issues when energy storage systems are used as ancillary services? There are a couple of FERC orders, 750. This is Federal Energy Regulatory Commission in US. 755 and 784, they provide incentives for fast ramps. The system operator dilemma is as follows. There's a trade-off between high ramp rate and high cost. So the system operator wants resources which provide high ramp rate because it can compensate for the vagaries of renewable generators without much of complexity, but then it has to provide for high costs for payment towards these batteries. So it can come as capex, or if there's a private party which has established energy storage, it can ask for a high capability payment for the same. Then effect on cycling of conventional generators. So the flexibility that these ancillary services provide, they can arrest the reduction in life of conventional plants because of cycling. And this is the flexibility that they provide. Question is, how do you really quantify this flexibility, and how do you really compensate or reward for the same? This is an open challenge in front of the policymakers. What happens to high ramp marginal cost conventional generators? So there are conventional generators like CCGT plants or gas-based plants, which can provide high ramp rates compared to conventional thermal steam power plants, right? What happens to them? That is the question when you have large-scale energy storage systems. And whether the ESS should be used for standalone ancillary or combined operation of other services. That is the question that is being used. If you take example of PJM ISO, how does it clear the market? So day ahead, D-1 means day ahead, between 12 p.m. to 4 p.m., what happens is the day ahead market is closed for energy as well as regulation. So no more bids can be provided. Complex bids have already been provided. And this software, which was discussed earlier, it calculates for the schedule and all that and comes out with the results. So the co-optimization of energy and reserves is carried out by the PJM. Now the challenging question is how to decide capacity payment of ESS because of their high marginal cost. How to account for that in this market clearing process is the real challenge in front of the system operator in PJM. Then secondly, if you look at the real-time operation, 60 minutes, that means 1 hour prior to the actual dispatch of generators, the regulation requirement is calculated by the system operator, and regulation market clearing price is also calculated 1 hour ahead of that. From ESS point of view, the question is how it should bid into the market. If it bids for very high cost, high marginal cost, then it may not get selected. And if the sole purpose of that ESS is to provide ancillary, then the whole purpose is gone. It will not be selected. And then if it provides for low bid, then how does it get compensated for the high ramp rates? That is another challenge from both ESS as well as system operator point of view. So there is something called as dynamic reserve activation. Basically, it involves procurement of reserve through market mechanism, and then there is an optimal reserve deployment plan. So if something goes wrong, if contingency takes place, then the system operator provides for this reserves, and there is a deployment plan associated with it. Extremely fast ramps provided by ESS, and that is of course considered. And there's a coordinated action of fast and slow reserves. So immediately after fault takes place or contingency takes place, the fast ramps come into picture immediately, and those are replaced by slow ramp units later on. So there's an optimization that takes place, which has got technical as well as commercial aspects. Those are getting embedded into the optimization that is carried out. And so long as now ESS are concerned, there are two kinds of issues related to it. One is market related activities and operational activity. So under market activity, there's a requirement of new product development for ESS, procurement of modalities for ESS, that is design. This is a design aspect basically. And how do we settle for fast ramps? These are three regulatory challenges which have come up. People are discussing about the same at length. And there are a certain set of operational activity challenges, which I will skip at this stage. Okay, I just skip this part as well and now directly jump to this distribution side considerations. Now, this is very important discussion. When you have large scale distribution, a new set of distribution system embedded entities are envisaged. Now, one must understand that we have so far discussed about the vagaries associated with the renewables and how or why should they should be considered when we talk about market clearing, ancillary services, market architecture, market design, etc. Please note that the renewables are not only utility scale renewables, but they are also getting embedded within the distribution systems as well. That is very important. Now, what do I mean by this? This is very important. When any plan is being made for establishment of renewables at large, then the utility scale as well as behind the meter kind of distributed renewable energy resources are also planned. Now, for example, India has got a target of 500 gigawatts of renewables installed capacity by 2030. That is the plan. Out of this, about 100 to 150 gigawatts will be solar rooftop. That means it will be on rooftops of households or big institutes. And basically, the generation of those solar PV rooftops will be embedded within the distribution system itself. And it will not be at the high voltage level at the transmission system. So this is going to be kind of behind the meter. Of course, through net metering and all that, the system operator will get to know how much is being produced. That's fine. But then you can imagine the kind of challenges that it might pose to the system operator at a distribution level. So far, what we have been discussing was the challenges for the system operator at the transmission level. Now, what is being offered by low voltage network in the changing context that you must understand? So you have transmission, you have a distribution transformer, and green power is being fed to the load, which is shown on the right hand side. And the right hand side, if you see the composition of the same, which is shown at the bottom. So you have demand response. Now the consumers, they are now responsive. So that means they are ready to change their consumption and the pattern of the same, depending on certain price signals. Then you will have large scale EVs and their aggregators. You will have storage, you will have smart buildings and clean electrification of the loads. So all this gets embedded within the distribution system. And together, DR, EV and storage, they can provide flexibility to the system operator at the distribution level, which it in turn can offer the flexibility to the transmission system operator. That you must appreciate. Okay, so this is a changing canvas of low voltage network. Now, how do distribution systems, they would transform when you have change in energy consumption pattern. So on the left hand side, you have distribution systems of today within certain regulatory framework. Now this network is by and large passive network. Okay. The distribution system of tomorrow is shown on the right top, which will be by and large active distribution network. That means there'll be a bidirectional flow from the distribution transformer to load and from load to distribution transformer and above. What are the characteristic features of distribution system of tomorrow? You will have e-mobility, storage, demand response, distributed energy resources, centralized and decentralized operation, and very, very important, you'll have retail level markets. Okay. So as of now, almost all systems, they have wholesale level markets. Very few of them, or none of them rather, they have retail level markets. But in the future, you are likely to have retail level markets. What does that mean? That means I, as a household owner, if I have solar PV rooftop and a battery storage as part of inverter, I can sell my power. I can make a contract with my neighbor under certain market framework, or I can sell this power to the utility itself. As of today, net metering is being done. Okay, but tomorrow I will have access to the market itself at the retail level. And why retail level? Why only retail level? Through TSO DSO coordination, I can have access to the market at the global level itself. So that is likely to come tomorrow. So the most important is you will have retail level markets in which you may have peer-to-peer transactive framework, or you may have a market administered by what is known as distribution system operator at the retail level itself, right? So this is the distribution system of tomorrow, having retail markets themselves. If you want to move from this to this, then you need to bring in infrastructural changes. You need to redo reorganization of entities. You need to bring regulatory changes and all that. So the anticipated changes are shown over here. At least in the Indian case, I can show this, that on the left-hand side, you have conventional consumers. The power used to flow from generators to National Load Dispatch Center to State Load Dispatch Center and to DISCOMs. That's fine. But tomorrow, the consumer is no more going to be consumer. The consumer is going to be prosumer. That means at times it can consume energy, at times it can generate electrical power through solar rooftop and sell it across through market mechanism, right? You will have EVs, solar generation, etc. And then to take care of all this, you will have retailers, you will have qualified coordinating agencies to take care of the renewables, and you will have aggregators to take care of a group of prosumers, right? And then since they would want to trade commodities across, a DSO may be required to be in place, who will take part in the power exchange at wholesale level. The aggregators themselves, they can take part in power exchange at wholesale level or at the retail energy and local flexibility market, and so on and so forth. So the characteristic is going to change, and it will introduce new key stakeholders as well. So the DISCOMs, that is distribution companies, will get converted into distribution system operators. For open access customers, you will have aggregators, you will have prosumers, retailers, and more importantly, you will have local energy and flexibility markets. So the entities embedded within the distribution system, they will not only trade energy, but they will also trade a flexibility. That is very important. You must keep this in mind. So to take care of all this, you need what is known as distribution system operator, or a DSO. Now, the changing scenario of distribution system, the portfolio of system operator is going to expand like anything. And you need a specialized entity which could be a transformed conventional distribution company or a new entity altogether to take care of the increased or enhanced portfolio of activities because of these renewables and the associated market actions, right? So in India, at least, and of course in Europe, there is a large scale discussion that is happening for introduction of DSOs, distribution system operators. It is expected that it will bring fairness and transparency because now you are giving open access to almost every entity in the entire chain of hierarchy of power systems, right? This DSO will enable the distribution level energy and flexibility markets. That is very important, and it will also promote retail competition. So the buzzword around the world these days is DSO, distribution system operator. Europeans, they have taken lead in establishing this. There's a discussion happening in US as well, and there is discussion happening in India as well. So this DSO evolution is being taking place in different parts of the world, but I'll not spend time on this. You may have a look at this later on. So long as establishing DSO is concerned, institutional framework needs to be defined. That is how to create a new entity, whether to convert existing entity into DSO, whether carriage and content separation needs to be there or not. So these are the discussions that happen under this title of institutional framework. How do you have market models in DSO? In what way? Do you have Dso centric model, or you have joint coordination model, or you have ancillary and flexibility services, centralized, decentralized decision making? How this flexibility, they are quantified and priced? So many questions. And there is horde of DSO functions which couple the conventional system operation tasks with the market operation tasks, because tomorrow you are bound to have retail markets for commodity and flexibility when you have large scale renewables, storage, EVs, DRs getting embedded into the distribution system. So there is something called as TSO-DSO coordination, transmission system and distribution system coordination, which is very important so that the entities embedded within the distribution system, they have got access to the global market. They are not confined only to the retail market. Through appropriate DSO and TSO coordination mechanism. Now, again, this topic is being discussed and researched about at large in the entire world. Through this appropriate TSO and DSO coordination, the commodities of the entities, electricity commodities like energy and all flexibility commodities like related to ancillary services, they can get access to the global or the wholesale markets through what is known as TSO-DSO coordination. To establish the framework for the same, you have what is known as TSO-DSO coordination. Okay, so if you have day-ahead market consideration, then this slide shows how it happens. What basically happens is that the commodities of DSO markets, they are cleared by a retail market entity, and the outcome of the same is passed on to the wholesale market. The wholesale market is cleared, taking cognizance of this, and then this procedure happens in iterative fashion so that there is a equilibrium between the outcomes of TSO and the wholesale market and the retail market. There are different coordination schemes for the ancillary service models. 5 of them, they have been provided or proposed by the European systems. The common TSO-DSO market model is shown over here. The difference between the two is that in this common TSO-DSO market model, the distributed energy resources, they pass on the commodities through aggregator to DSO, and the flexible resources, they directly go to the TSO, and there is a interaction between TSO and DSO for global market clearing procedure. So long as market models are concerned, there are two models that are being proposed. One is Dso Centric Model and the other is Joint Coordination Model. The quick difference, if I have to tell you, between the two models is that in Joint Coordination Model, the entities embedded within the distribution system, they can take part either in wholesale market or DSO market for their commodities. But in Dso Centric Model, if the entities they want to take part in wholesale market, they have to go through the DSO itself. They cannot directly go to the wholesale market. So there is a framework defined for both of this. Now let me come to the last part of the discussion, and I'll just quickly talk about the Indian scenario, what is happening on this front, and then I'll stop. Just to give you a brief idea of what Indian system is, the size and the same, you can see on the left-hand side that there are 5 regional grids. So the whole country is divided from the operations and the commercial settlement point of view into 5 regions, regional grids: north, south, west, east, and northeast grids. And of course, from the system operation point of view, the entire grid is just one grid. From it's a synchronous grid. One country, one grid is what we say. The annual per capita consumption is of the tune of 1200 kilowatt hour units. Peak demand that was served recently was more than 200 gigawatts. And the installed capacity of generation is 390 gigawatts, out of which thermal is around 60%, and the renewables is of the tune of 26% as of now. The renewable installed capacity targets, they have been revised recently by our Honorable Prime Minister in COP26. Earlier it was 450 gigawatts, which in itself is a very ambitious target. Now, the Prime Minister further extended it to 500 gigawatts by 2060, and it is expected that 60% of the installed capacity will come from the renewables, which is a huge, very ambitious target, and of course, would pose challenges from the system operation point of view as well. Now, the kind of transactions that happen, or so long as Indian power market is concerned, what type of trading mechanisms that are available to the stakeholders? There are 3 types of trading mechanisms: long-term, medium-term, and short-term. So long-term are of the order of more than 20 years. Medium-term is somewhere between 6 months to 10 years, I guess. And short-term are, it could be day ahead or term ahead, etc., or real time, etc. Now, in short term, you have bilateral transactions that happen through the traders. You have various products provided by power exchanges, and you have something known as deviation settlement mechanism, which acts as a real-time incentivizing or penalizing mechanism for the deviations that you create. So long as power exchange products are concerned, you can divide them into 3 parts. One is day-ahead market, wherein this market is, so these are basically energy markets. So you have day-ahead market. It's a closed double-side auction. 15-minute is the granularity. Term ahead markets, there are various products that are available. It could be day-ahead contingency, intraday, and weekly market as well. And there's one interesting thing called renewable energy certificates. So all states in the country, they have been given target of renewable purchase obligation. So certain portfolio, certain part of their energy procurement portfolio should come from renewables. That is what is called as RPO, renewable purchase obligation. Now, some states, they would produce more power through renewable sources than what is RPO, and some states would be deficit in terms of RPO production. So those states who produce more power compared to what they are supposed to provide, the extra power gets converted into what is known as renewable energy certificate or REC. So 1 megawatt hour is 1 REC. And these RECs, they can be traded on power exchanges. So those states who are deficit in meeting that RPO, they can buy those RECs on power exchange. That is another product floated by power exchange. Now, achieving this target of 500 gigawatts, there are multiple challenges, issues, and the remedies associated with them. The challenges can be divided into 4 types of challenges: investment challenges, whether it should be government investment or private investment; operational challenges, as I said, ramps, congestion, etc. These are operational challenges. There are challenges on policy and regulatory front, that is grid code, markets, rooftop solar, what should be the policy for the same, what should be the incentives for the same, etc. And planning problems. Now, the remedies come from 3 aspects. One is the technical solutions to achieve this. One is, of course, the policy and regulatory, and third is the market. So if you devise appropriate market products, you are likely to get appropriate response from the private players, so that this target of 500 gigawatts can be achieved. Now, to achieve this target of 500 gigawatts, there needs to be organizational ecosystem in place. What are the key drivers? So I have divided them into 5 key drivers. One is competitive bidding, which will bring participation of private players. So Solar Energy Corporation of India, SECI, recently, or rather it has been following this competitive bidding for establishing solar farms, right? And it has been quite successful, and it has got equity from the private players. Policy and regulatory, there is ancillary services, waiver of transmission usage charges for renewables is another key driver, which is bringing in the private participation of for renewable generators. Green energy corridor is being established to evacuate power from the renewables at the utility scale. Ministry of New and Renewable Energy, it has got many initiatives like subsidies on renewables, zero import duties on capital equipment associated with renewables, low interest tax exemptions, etc. And there is a mandatory procurement of real power, renewable power, that is through RPO and RAC. So these are the organizational ecosystem key drivers which are driving the demand and supply of renewable power, so that we achieve the target of 500 gigawatts by 2030. And I think I should stop here, because it's exactly 1.5 hours that I have taken. Thank you for patient listening. I would like to now answer.
Recording in.
I would like to answer questions now. So there's one question: is there any practical situation where ESS has been used for black start? Okay, so that's a good question. So long as my knowledge goes, Dailini, Fernando, I have no idea. I mean, at least to me, my knowledge, there is no such incidents that has taken place where ESS has been used for a black start. But nevertheless, you can appreciate that a large-scale ESS can really be useful, rather than depending on hydro stations or diesel generators, etc. ESS can also, I mean, this is another byproduct that it can provide, so long as establishment of ESS is concerned. Yeah. Are there any other questions from the participants?
Thank you so much for very informative and insightful talk on this topic. I think there is no further question from the participants.
Yeah, so yeah, I appreciate your patient listening, all participants. And If you have any questions, please don't hesitate to send me a message on my email. I'll be happy to respond to the same.
Thank you so much, sir.
Thank you, Professor Abhyankar. Thank you very much. And to all the participants, we have a leave. We will break for about an hour and we will resume at 2 p.m. India times. So after an hour. Thank you, Professor Abhyankar. Thank you very much.
Thank you. Namaste.
Namaste.
I think I can leave now, right?
Yes, sir.
Yes, please.
Yeah.
Yeah.
Thank you.
Yeah.